I lied. I fucking lied. This shit's not easy. But I will say, committing something to memory is way easier when shit actually makes sense rather than just trying to brute force memorize all the components of the pathways. And that's how you have to approach these complicated biochemistry pathways in general. You have to really pick apart every step and make sure that you understand what's going on. The purpose of this video is to walk you through the 10 steps of glycolysis slowly and thoroughly. Wipe that terrified look off your face. We'll be fine, alright? We'll survive. If you hear screaming in the background, first of all, I hope you don't, but if you do, no one is dying, or maybe someone is. I happen to be an RA in a freshman dorm, and it happens to be the weekend before Hollow Weekend. My freshmen are going feral, bro. Holy. Alright, so we're gonna start with the first step, and we're gonna start with our glucose. So whenever you're working with sugars, it's always a really good idea to number them. So since it's a sugar, every carbon is going to be hydrated, mean that it's gonna have an OH group. Now the first reaction is that we're gonna phosphorylate this glucose. Anytime throughout the glycolysis pathway, if you have an instance where you're phosphorylating something, two things to remember. Number one, it's always going to be done by some sort of kinase. And number two, it's going to be irreversible. Now, technically, is it completely irreversible? No, like it is kind of reversible, but this step is so energetically unfavorable that we just say that it's irreversible. Now, why that is important is that every other step in the glycolysis pathway is going to be reversible. So the only points where we can do some actual regulations in controlling how much shit is being made are the points where it's irreversible. So that's why that's important to remember, but that's not really the point of this video. The point of this video is to walk you through the glycolysis pathway itself. So just remember that it's going to be irreversible and some sort of kinase is going to do it, right? So in this case, the kinase that's going to phosphorylate the glucose is going to be hexokinase. Now, anytime you have an enzyme, always look to its name to figure out what it's doing. So we have hexokinase. Obviously, kinase, it's going to be some sort of transferase that transfers a phosphate group from one molecule to another. In this case, it's transferring the phosphate group on an ATP to the glucose, right? So we're gonna invest an ATP and we're gonna end up with an ADP. And that phosphate group is going to end up on the glucose. Now hexo. Notice how it's hexokinase, not glucokinase. Now this is because the hexokinase is actually able to do this shit not just with glucose, but with any other kind of hexose. So it has very broad substrate specificity. So once we phosphorylate this glucose, we're going to end up with a glucose 6-phosphate. Which means that we're going to have a glucose molecule that has a phosphate group on carbon number 6. So that's reaction 1. Done and simple. Now in the second reaction, we're actually going to have this glucose molecule, this glucose 6-phosphatate, turn into one of its isomers, specifically a fructose. And the enzyme that does this is the phosphoglucose isomerase. Again, look to the name, phosphoglucose. So it's going to be a glucose with a phosphate group, phosphoglucose isomerase. It's going to turn it into its isomer. So phosphoglucose isomerase. Shocker that enzyme that's going to do that is going to be called literally phosphoglucose isomerase, right? All right. So we're going to take this glucose 6-phosphatate molecule. We're going to do that because I'm lazy. Ugh, love technology. And the way that this enzyme goes about this is actually it's going to have to open up the cyclical ring in order to move around the substituents to make it into its isomer and then close it back up again. What I mean by that is that it's actually going to start by opening up the glucose 6-phosphatate. What would be more stable, the cyclical form of a sugar or the open chain form of a sugar? If you said cyclical, you'll be right. Congratulations. I don't know why that sounded sarcastic. I actually congratulate you. The cyclical form is more stable. So this means that the forward reaction is actually going to be unfavorable compared to the reverse reaction, right? So opening up this sugar, we don't like doing that, but we're going to have to do it anyways in order to move around shit to make it an isomer. So glucose is an aldose, and fructose is what we're turning this into. Fructose is a ketose. So an aldose is going to have an aldehyde group, right? So again, always number your carbons. Glucose is an aldose. Fructose is a ketose. So it's gonna look very similar, except it's gonna have a ketone group instead of an aldehyde group. So your ketone group is gonna be on carbon number 2. So that is gonna be your fructose 6-phosphate. We're not done yet. We need to close that ring back up again, right? We need to close that open chain form of the sugar back into its ring form. Now again, the open chain form is going to be less stable than the ring form, which means that in this case, unlike our first instance where the reverse reaction was more favorable, the forward reaction is going to be more favorable, right? So do you see how in the entire grand scheme of things, because this step, the reverse reaction is more favorable, while in this step, the forward reaction is more stable. In the grand scheme of things, there is no favorability. This is just a reversible reaction. Once we close this ring back up, we're gonna get the ring form of fructose 6-phosphate. Beautiful. So now we have the isomer form of glucose 6-phosphate, which is fructose 6-phosphate. And the enzyme that did that is phosphoglucose isomerase. Now step 3, we're going to have another phosphorylation. Again, when we have a phosphorylation in the glycolysis pathway, we have a kinase that's going to do that and is going to be irreversible. In this case, the kinase that's going to phosphorylate fructose 6-phosphate is called phosphofructokinase. Personally, this is my favorite kinase, which makes me sound like such a fucking nerd. Holy shit, who has a favorite kinase? But something about the fruc being in there, I don't know. It just speaks to me. I like this kinase. Anyways, what it's gonna do is it's gonna phosphorylate this, right? So again, we have a irreversible reaction catalyzed by a kinase. So we went from a fructose 6-phosphate, and we have a phosphate group on carbon number 1, and we have a phosphate group on carbon number 6. So this is gonna be fructose 1,6 is phosphate. Nomenclature should be very intuitive here. We have 2 phosphate groups on carbon number 1 and 6 on our fructose. Good. So that's number 3. Step number 4, we're gonna cleave this shit. And when we cleave this molecule, we're gonna cleave it into 2 3-carbon membered molecules. And the enzyme that's gonna do this is an aldolase. Again, this isn't a phosphorylation, so everything is reversible. And an aldolase is going to cleave this into 2 molecules, respectively called DAP and GAP. Bro, this shit's so funny. DAP and GAP. Alright. So DAP looks like this. And GAP has an aldehyde group. So at this point in the reaction, we have 1 DAP molecule and 1 GAP molecule. The thing about the DAP molecule is that it can't proceed in glycolysis. So we actually have to convert it into GAP. And the enzyme that does that is triose phosphate isomerase. Again, enzyme name correlates to function. Triose, what does that mean? We have 3 carbon sugars. So these are trioses. Phosphate, we have phosphate groups on the 3 carbon sugars. Isomerase. GAP and GAP are isomers of each other because it's just literally the fact that this has a ketone group while this has an aldehyde group. Their molecular formulas are the exact same. So a triose phosphate isomerase is going to be the thing that interconverts DAP into GAP. So at this point, we have 2 GAP molecules. But the reason I emphasize the 2 so much is that I'm just going to proceed with 1 GAP molecule from now on here, but realize that this is happening with 2 GAP molecules. So anytime we get an ATP, we're actually getting 2 ATP out of this. Okay? So I just want to make that really clear that we're working with 2 GAP molecules here. So everything subsequently that goes from here from the glycolysis pathway, we're doing it twice, or more so simultaneously with 2 molecules, right? Okay. So now we have 2 GAPs. So in reaction number 5, we're going to take the GAP molecule and we're going to oxidize it. The name of the enzyme that does this is, bear with me, glyceraldehyde 3-phosphate dehydrogenase. But realize that it's actually literally just a substrate name because GAP stands for what? Glyceraldehyde 3-phosphate, right? So the enzyme name is literally substrate plus what it does. Dehydrogenase. Take a wild guess on what it's going to do to the GAP molecule. Dehydrogenase, right? Dehydrogenase. So it's going to get rid of dehydrogen, right? So the end product looks something like this. So I'm going to kick that. It's going to replace it with a phosphate group. And the name of this molecule would be what? So we have a phosphate group on carbon number 1. We have a phosphate group on carbon number 3, right? So this is going to be 1,3 bisphosphoglycerate. Realize that we went from a glyceraldehyde to a glycerate because we don't have an aldehyde group on this molecule anymore, right? The mechanism as to which this happens is actually very much worth looking at because this is actually going to use NAD plus converted into NADH by taking that hydrogen, and it's also going to have a phosphate group involved. I'm going to make a separate video on how exactly the dehydrogenase does this because the mechanism is worth looking at because the intermediates has a lot to do with like lowering activation energy, and it's pretty important. But for now, since we're just doing an overall walkthrough, so if you take a good look at our 1,3 bisphosphoglycerate, right, we have two really high energy phosphate groups on a really small molecule here. So the interesting thing about this molecule is that it's elated to give off its phosphate groups, which is great for us because any molecule that's elated to give off its phosphate group, we can literally transfer it onto an ADP and make ATP, i.e. make energy, right? That's exactly what step 6 is about. So step 6, we're going to take this high phosphoryl transfer potential to power ATP synthesis, meaning that we're going to make some ATP. And that's going to come from one of these phosphate groups. Now, it's a phosphate group transfer. What enzyme is going to do that? It's going to be a kinase, right? It's phosphoglycerate kinase. Again, we just take the substrate name and it's a kinase. So phosphoglycerate kinase is going to be the enzyme that does this transfer. And we're going to end up with a glycerate. Notice this is the first time we ever got something back from this whole step, right? Because so far we've only invested ATP. We invested ATP twice. This is the first time we actually made ATP. And remember, we're doing this with 2 gap molecules earlier, right? If you scroll up, or if I scroll up and you watch me scroll up and watch me struggle to find what the fuck I'm looking for. All right, here. If you recall, we made 2 gap molecules because we converted DAP into GAP, right? So we're doing this whole thing with 2 gap molecules. So technically, in terms of like the entire glycolysis pathway, we got 2 ATP molecules since we're doing this with 2 of these, right? So we got 2 ATP. So keep that in the back of your mind. Again, name should be intuitive. We have a phosphate group on carbon number 3, and we're working with a glycerate now, right? So step number 7, we're going to take this 3-phosphoglycerate, and we're going to turn it into another isomer form, which is 2-phosphoglycerate. Now, given these names, take a wild guess on what this is going to look like, right? So we're going to take this molecule, and we're going to swap the position of the phosphate group to carbon number 2. So that's essentially what this reaction is doing. And the name of the enzyme that's going to do this is a phosphoglycerate mutase. Now, this nomenclature of the enzyme might be tripping you up because up to this point, anytime we did anything like this, we called it an isomerase. A mutase is a type of isomerase. So I like to think of it as mutase. So you're mutating something, right? So you're changing something. So you're literally just moving this group up there, this group down here. Again, the enzyme mechanisms of this is worth looking at. I'll make a separate video for it. But for now, just know that phosphoglycerate mutase, again, phosphoglycerate, literally just a substrate name. And what does it do? It mutates it, mutase. So phosphoglycerate mutase is going to swap out the phosphate group on carbon number 3 to be on carbon number 2. So step number 8, we're going to take 2-phosphoglycerate and we're going to make it into its enolate form. Now, I know, I'm making you recall your organic chemistry days. Holy shit, bro. Literally the trenches. I know, but unfortunately it has come back to haunt us. If you do not remember, this is a ketone. Honestly, if you don't remember what a ketone is, you're low-key cooked. And its enolate form, that's an enol, right? Ketone, enol. And these are in constant equilibrium of each other. Same thing. We're going to take an enolate. And it's worth noting that this is a dehydration reaction, so we're going to lose water. Where does that water come from? It's going to be this thing that's going to leave. So this is going to be our phosphoenol pyruvate. The end is near. We finally got to something that remotely looks like our pyruvate. And remember, we're doing all of this to make a fucking pyruvate. So we're so close, bro. Reaction number 9. So reaction number 9 involves a phosphorylation. And whenever we have phosphorylation involved in glycolysis, what do? We use a kinase, and it has to be irreversible, right? So the kinase that's involved in this, really freaking easy. It's pyruvate kinase. So pyruvate kinase. In this case, we're going to take this phosphate group and we're going to put it onto an ADP. So pyruvate kinase is going to fuel the synthesis of ATP by moving the phosphate group on carbon number 2 of phosphoenol pyruvate to an ADP to make ATP. Good? Which gives us the enol form of our final product. And then this is reaction number 10. This is just going to tautomerize. How the fuck do you say that? Tautomerize into pyruvate. Alright, my camera battery died as soon as I said pyruvate, which was really freaking satisfying. As much as I want to just end the video here, I do think we need to talk about what energy we spent and what energy we got. So step 1, we phosphorylated a glucose molecule. And that took an ATP, right? Because we needed the phosphate group in order to do that. So we used 1 ATP here, right? Similarly, we also phosphorylated using a kinase, a fructose phosphate, right? So this phosphate group came from an ATP. And phosphofructokinase is the thing that did that. So we also used 1 ATP here. So how much ATP total did we use? 1 plus 1 equals 2. If you can't do that, you're cooked, drop out of biochem. 2 ATP. We used 2 ATP. All right. So let's scroll, and let's find our kinases, because kinases, is that how you would pronounce that? I don't know. Kinases, plural, whatever. Kinase, to see when we got ATP here. So reaction number 6, where we took the phosphate group on a gap molecule and we transferred it onto an ADP to synthesize ATP, we made 2 ATP molecules total, because remember, we're doing this twice with 2 gap molecules. So we got 2 ATP here. And similarly, again, look for your kinases, because that's where ATP and ADP probably interconverted. We have our final kinase here, pyruvate kinase, where we took the phosphate group on phosphoenol pyruvate and we transferred it onto an ADP to make ATP. Again, we're doing this with 2 molecules of phosphoenol pyruvate. So we got 2 ATP total. So if we got 2 ATP from this reaction and we got 2 ATP from this reaction, how much ATP total did we get? 2 plus 2 equals 4. So we got 4 ATP. So in this case, we used a total of 2 ATP. Didn't mean to delete that. 2 ATP. And then we got 4 ATP here, which gives us a net gain of 2 ATP. Is that a lot of ATP? Absolutely not. That is barely anything. So glycolysis gives us the very, very little ATP that we need. The rest of the ATP that comes from cellular respiration comes from your electric transfer chains, the Krebs cycle, etc. Definitely a video for another time. But for now, just know where the ATP is spent and where we get the ATP energy. The glycolysis pathway is generally described in two stages, the energy investment stage and what I like to call the money getting stage, where you actually get that energy back. So everything up to the point where we are using ATP, which is up to the point where we phosphorylate our fructokinase and then use ATP. This is the investment stage where we're investing energy, and the rest is where we're actually getting our energy back. And that's glycolysis.